Okay, so we have a spectra here, and this spectra we discussed in the class came from the homework assignment. Homework assignment B15 and 15.9b. So when we look at the spectra, we have to identify how many different protons we have, or types of protons we have. Because it's very simple. We have only 1, 2, 3 different protons, and we have the area count for them. So let's go see if we can predict based on what we know about the spectra. We know it has four carbons, 6 hydrogen, and 2 oxygen. And the index is 2. The efficiency is 2. So either has a C double bond O and a ring, or could be 2 rings. But if you have 2 rings, then we don't have enough carbon to make 2 rings. So most likely it's 1 ring because we only have 4 carbons and 2 oxygen. So let's see what we can predict or propose for the structure. But before doing the structure, we need to look at the uh, splitting, and from the splitting, we can have a good idea of what's going on. Again, the index is 2. So we have a cyclic, we have a most likely a C double bond O counts for 1, and the O which doesn't really count anything. So if I look at the area, I'll take the smallest area, which is 18.92, divide everything by 18.92, and you can see they are very similar. So if they're all 1 and 1 and 1, we need to have 6 hydrogen or protons. We only have 3 here, so we multiply by 2. Now we have 2, 2, and a 2. So I put a 2 here, 2 here, and 2 here. So that adds up to 6 that we have for this structure. Now, of course, oxygen doesn't show anything, but the oxygen influences the ppm that we have here. So let's look at a little bit more details about the splitting pattern. If I look at the splitting pattern for these, so I can see that we start with A. Remember, we put an A here, B, and a C. A has a signal of 5 signal. So if the A is here to become a pentate or 5 signal, we have to have 4 protons next to it, basically 2 CH2. So that makes 4 plus 1 is 5. Now, if I subtract 2.4, which was given to us, from 1.2, which is a typical CH2, I have additional ppm 1.2. At this point, I'm not 100% sure where does that 1.2 came from. So we leave it alone for time being and go to B and C. In B, we know we have 2 protons. We know that for that to become 2.6 or 2.2, let's say 2.2, we need to add 1 ppm to it from the C double bond O. So we get 2.2. It's not too bad because 2.2 is really what we calculated. And 2.6 is actual. So the actual is a little bit more than 2.2. That's fine. Now we go to the last proton, C, which is blue. Draw it as a blue here. So that's really matches very well. So if you have a CH2 next to a CH2, so that means 1.2 plus 3 ppm. So that means really it has to be next to an oxygen. So now it's 4.2. It's really very close to 4.4. That we have the actual is 4.4. So far we have done well, except the A. We're a little bit iffy on the A, but we know B and C for sure. So let's propose a structure and see what we can do for the structure. If it's a cyclic, we have a C double bond O and a O. So that's really a lactone. So this is a lactone. And we look at the lactone as a C double bond O. Oh, sorry, here, not a good one here. So we have a C double bond O, and that C double bond O, part of the ring has a O. So that's a lactone. So now let's go put them together. We know the blue one is we have a good idea of the blue one. Again, I repeat the spectra here so I can look at it. And we have a good idea on the green one, so we can put those on first. So the blue one basically is the one that next to the O has the highest number, or is downfield. Remember this with downfield here. So that's 4.4, 4.4. And it's next to a double 2 partons. So again, it's a triple here, right? We show. Then green one, let's look at the green one. Green one is a triplet. And that's next to the C double bond O, so that ppm pretty good close to it. So we have to go back now to this. Basically, we have 4 carbons. 1, 2, 3, 4. So this carbon, the fourth carbon, has 2 H's. Again, we have 1.2. So we went from a 1.2 to 2.4. So we added some ppm to it. That's okay. That's okay. And that's from the influence from the oxygen and C double bond O. So that's really our lactone. It's called beta lactone, 4-member ring lactone. So that's really the chemical structure. So let's look at the opposite. If I have that lactone and I want to go from lactone to proton NMR, that's actually a lot easier to go from the chemical structure to predicting what the NMR of that is going to be, especially for a simple thing like this. So I draw my lactone. Again, I put a green, purple, and blue here. I started with the blue. I said it's 2 H's next to the O. So I put 3 ppm to add it, 4.2. 2 H's is green. I added 1 ppm for the C double bond O, 2.2. And the purple one, I wasn't sure. So I add 0.5 or maybe 0.7 for O and the C double bond O. Again, on extended version, not next to them, but close enough. So there is some influence. So would be I predicted would be 1.7. Then I went back through that. You can just start from A to B or C to B A. So we have A. So A would be pentate at 1.7. Then we have a B at 2.2 and C as 4.2. Very close to what the actual NMR was. And you need to practice more.